So I'm done with perturbation theory and Feynman diagrams and so on. We're going to look at another type of approximation today, which is like a mean field theory. And I mean, if you do condensed matter, you'll be familiar with mean field theories. We're going to just motivate them from the path integral, and then I'm going to talk a little bit about the Laudau theory of phase transitions. So just for the sake of, I guess, concreteness, remember the single particle path integral. The thing I called the propagator, which was a functional integral, something like this. For the single particle case. And of course the action, S, with some integral over time. Which we're calling a Lagrangian. Maybe something like this. Where there's no momentum anymore, it's been integrated out. So this, this path integral expression has no, as we know, approximations in it, in principle, once you're in this functional integral notation. But the difficulty we have is in solving this thing, right? And what we saw last time is when we have the case of interactions, we have these 5-4 fields and so on. We can develop a perturbation theory to get sort of approximate solutions. And what we're going to look at is just general approximate solutions now for in the case when we basically can't do this sort of full integral, okay, or this functional integral, which is an integral over all possible basically Feynman paths. So let's look at a semi-classical approach. And I call it semi-classical because the full quantum mechanics is, of course, contained within that functional integration. And as I've alluded to this before in this class, when you don't take that integral, you can basically just look at the classical action and use it as an approximation for the full quantum expression in some cases. So the basic, I guess, mathematical approximation behind looking at the action without that integral is this called the saddle point approximation. And we can develop it outside of the context of that functional integral, just like we did for Gaussian integration. We looked at an integral, then we looked at a Gaussian integral over many variables, and you keep just generalizing it and generalizing it till you're in the functional integral case. So consider first just some simple integral that is integrand, I don't know, some function of x. And you should be thinking of that n is something like this parameter in front of the action, say. And if h bar is very small, then n could be something very big. And then we'll consider that limit so that we can essentially Taylor expand what's in that exponential. So now if that function has a certain minimum in it, so I don't know, as a function of x, f of x could have some minimum around some value, which I'll call x bar. Then e to the minus n f of x will look like, I don't know, something like this. It'll be peaked around that same value of x bar. And when you integrate over all x, then the biggest contribution of that integral will occur near that peak, near that maximum value of the function. Okay, so if we concentrate near that maximum, so say the minimum of f, and note because this is a minima, then the first derivative of the function evaluated at x will be 0. And if I assume we're concave up, which I'll justify a bit later, then the second derivative has to be positive. Then we can take this integral and write it with the Taylor expansion. So just the value of f, the function at that minimum, x bar. My first derivative is 0. I'll get something like the second derivative times x minus x bar squared. And I could keep going. dx, yeah, that's right. Okay, in this function, evaluated at that minimum value, it's just a scalar. This is just another number, right? So I essentially just have a Gaussian integral over x minus x bar. So an approximate expression for this integral, and it's approximate because I've thrown out higher order terms. So again, this might be accurate to sort of various degrees, depending on what your function looks like. It'll just be something like this. And quite generally, this prefactor, which is 2 pi n, that parameter f double prime evaluated at x bar, this thing's just some constant. So if I'm interpreting this integral eventually as some sort of partition function or something like that, something that gives me, say, a free energy, then this thing isn't going to be the thing that matters. There'll just be some constant prefactor out front. This will give you sort of the bulk of the interesting behavior. So then I'm not going to say well approximated because it depends on the form of the function. Just the integral is approximated by the maximum value of the integrand. That type of approximation is sort of the essence of mean field theory. So it is an approximation, and whether or not it's a good approximation sort of depends a lot on the specific problem that you're looking at. So this is the idea we're going to sort of run with in today's class. We're essentially going to look at just the value of the integrand in that path integral. Okay? And we hope that the behavior is sort of dominated by this minimum in the function f. So let's go back to our original action just for a minute. Just to build some intuition for what we're going to derive. So we've done already, as we've done already in this class, we can imagine finding the minimum, right, which is like the minimum of this function here, by taking that derivative. And in this case, sort of it's simple, but when you have functionals, right, then you have to basically look at the variation of the action, because it's like the fields are also functions, right? So the action's a function of phi, the fields are a function of x's, sorry. So the minimum is found by taking a variation of that action and setting it to 0. Yep.
So this approximation works if you go to usually you have time, right? Because that I up there matters if you're
Yeah.
you have time.
Yeah. So I should always be thinking of this basically as a partition function.
Okay.
Yeah. So let's just imagine that's what we're calculating, because that's actually what we're going to do. So the minimum, yeah, so this is Euclidean time action now. So the minimum is found by taking the variation and setting it to 0. So it's like, which in this case is basically just an integral. Okay, so if you take the integral of the, so finding the variation of the action and setting it to 0 is the same as taking the first derivative of the Lagrangian in this case. Okay, so it's we're just rederiving like first year physics somehow. So it's MA is equal to V, the derivative of the potential in the way that I've written it. And if you set the acceleration, right, to 0, then you're just finding the equilibrium value. That's your simplest sort of equation of motion, right? That comes out of varying the action. So nothing deep. Something you already know from classical mechanics. But now let's look at our phi-4 theory. Okay, so now we're going to replace our action with the Euclidean action for the scalar field. So S of phi okay, so I have a half in front of actually both of these terms. And this is my interaction term. Right? So similarly, I want to find, in order to use the saddle point approximation, I want to find the minimum of that action. So the phi value, right, that gives me the minimum. So phi is a function of your d+1 coordinate system, or what I'm calling small d. And it can vary everywhere within that higher dimensional space. But just like I set, you know, my x to be, you know, I guess my acceleration to be 0, and I've looked for, you know, mean value of x around that minimum. I can set phi to be space-time independent and look for the minimum, resulting minimum of that action, because as you should consider on your next assignment, or is it the assignment you have now, assignment 4, this thing will just essentially raise your energy. It'll raise your free energy. It'll give you positive contributions to your action. So if I set phi, x just equal to phi, then what we're deriving is something that only has to do with the sort of mean or average values of the fields. And this is why it's called a mean field theory. Okay, so we're no longer considering sort of all the space-time dependence of the fields. We're just looking at what it does on average. So we can take this Lagrangian density, and do the same sort of minimization as we did in this step here.
The meeting has ended because it had only one participant for the last 30 minutes.
Weird. So what is this thing? It's so in the case where we don't have any spatial variations, it's just r over 2 phi squared plus u over 4 phi 4. And taking the variation of the action corresponds to the equation This is basically what you're doing on assignment 4, question 2. All right, so you're basically just deriving sort of the equation of motion in this very simplified case that corresponds to like a mean field theory. So the solution to this equation gives the vacuum state of the system. Which is just the value of the field corresponding to this minimum. And if you look at that equation, you say, well, it's always, phi equals 0. But that's not always the case. It depends on the sign of R and U. Right? And that's what you'll see when you do the assignment. Right, so. I'll probably call it V, right? Yeah, so it's phi bar equals V for vacuum state. So it's just the solution to that equation. And note it's not always necessarily phi bar equals 0. And when it's not 0, this is the case of symmetry breaking. I'm going to come back to symmetry breaking in just a minute. So before that, just let me remember what is going on in the rest of this assignment question. I think what you do is you consider variations around the vacuum value. I don't have a copy. So once you have this mean field value, this sort of constant value, you can also consider fluctuations around it. They call it the Gaussian theory, Gaussian fluctuations. So I'm going to leave that for your assignment. The first thing I asked for is probably the value of V, right, for this simple equation of motion. And then once you have that value of V, consider perturbations away from that value in the field. So it's like phi goes to V plus some field phi prime. And in the assignment, I say, you take that value for phi, and you plug that thing back into your full Lagrangian. And then you study the formula of the Lagrangian. And by the full Lagrangian, I mean put the spatial variations back in, the space-time variations. And when you look at the form of that Lagrangian, the term that's proportional to phi prime squared will give you the mass of the elementary excitations out of the vacuum. So sort of the philosophy with this mean field approximation is that you have a very low energy state. So you have a state that essentially has you sitting at the minimum of this function. And if you're thinking about the Euclidean path integral, this would be like your zero temperature state maybe. Or it could be your state without a whole bunch of fluctuations. But then if you can start to consider fluctuations around that state, you can induce, as you know from your assignments and so on, particle-like excitations out of the vacuum. And those particle-like excitations can have a mass. Okay? It's like your quasi-particles that, Caldeia found in that experiment in the transverse field Ising model. And the mass is proportional to the phi prime squared term. Why is it a mass? So that's a question we'll address now. But this is, again, sort of the philosophy of quasi-particle excitations, even in any sort of quantum many-body system. So even in something like condensed matter. This picture doesn't always hold. This idea that you excite elementary particles out of a vacuum and they have a well-defined quasi-particle structure. And it particularly doesn't hold when you're sitting exactly at a phase transition or a quantum critical point. So you really have to be careful with this. This is only sort of the simplest sort of theory of symmetry breaking in excitations. We'll talk more about it, but I just want to take a little aside into why it's called a mass. The phi squared term, that's the R. It's just some arbitrary parameter that it's either phenomenological. You just assume based on the symmetries of the system that you have that term, and then you figure out what that thing is from experiment or something like that. Or you can in principle derive that thing microscopically like you're doing with the Ising model. Okay, but it doesn't look like a mass at all. So let me rewrite the classical action. So let me rewrite the classical action here, just in terms of its Lagrangian. And that'll give us some insight. Okay, so I have no path integral. I just have S. I called it X, but I want to keep the time dependence in there. You could call them Q's, I guess. I just have a Lagrangian that has a time dependence. Yeah, that's it. And the coordinates, X or Q's. And I derived a very simple case of the equation of motion using that specific Lagrangian there. But if we have something more general than the equations of motion, or more general, and more generally, it's the Euler-Lagrange equations. So you have a time derivative acting on your coordinate derivative. I'm using curly L's here, man. Let's have some class. You get one of these equations for every coordinate that I've labeled J here. Okay? Again, just classical mechanics. If you have a classical action, you get your Euler-Lagrange equations of motion. So you're taking a time derivative of that coordinate, the derivative with respect to that coordinate minus that derivative again. So we can determine sort of generally what our equations of motion are for our phi-4 theory by using that Lagrangian over on that other chalkboard. So And actually, let me put in the full, I need the time dependence, right? So let me put in the full space-time symmetric Euclidean action. And the equations of motion actually are general enough that I don't think I need to restrict to just the Euclidean case. Off the top of my head, I don't think so. It just depends on basically the metric here. So let me be a little bit careful with that first derivative over the coordinate system. Okay, so in general, I'm going to write an analogy to the Euler-Lagrange equations. But see, I have q's here, and the analogy of q's will be my phi's. So I need derivatives with respect to phi's, but I also need derivatives. Here I only have a time, right? But in the phi-4 theory, I need basically derivatives with respect to every coordinate axis, x, y, z, and time, right? So you got to be a little bit more careful with that. So just so I don't get these partials confused with this, I can just label that with a coordinate. So I'd say d phi and I haven't been very careful in this class, but we can start to be with what exactly this means. So of course we have Wick rotations, which I've just been sweeping under the rug, but the Wick rotations affect the sign of these terms, right? Because you get an I, an imaginary number here, and you're squaring that to get a minus sign. But if I'm dealing in real time, then this thing looks like this, squared for all of your x, y, z, whatever dimension you're in. So quite generally, you can write the Euler-Lagrange equations in terms of these derivatives and fields. So I need derivatives over all those coordinates, not just time. And then I need a derivative of the Lagrangian with respect to the coordinate derivatives of the field. Yeah, that's ugly. So I'll keep that mu in there. And then the last term is just the derivative with respect to the field phi. I think that's right. I'm going to say yes. So this thing you have to be careful with, especially in terms of whether or not you have Wick rotated this. And this is, of course, just the sort of simplest, like flat space metric, Minkowski or Euclidean. So in other theories, this becomes something like, you have to worry about sort of what your metric looks like. So just let me say that there's an implied sum over indices here, just like there is here. So you have a time piece, derivative of Lagrangian with respect to the time derivative of the field. And then you have the first coordinate x, derivative with respect to the x, derivative of the field, and so on. Okay, so if you handle that term properly, then your Euler-Lagrange equations give you a very simple expression. And let me set u equals to 0. So now I'm just going to throw away all my interactions. Substitute L into the Euler-Lagrange equations. And what you'll see, you can basically see it from here, is that you'll have terms that are like, okay, so the equivalent of del squared. And then you're just subtracting off something proportional to r. And those 1/2s cancel from your taking the derivatives of those square terms. Right? So it's like the first term, you're taking a derivative here. This term, you're taking a derivative of that. Right? And they're partial derivatives. So what this means is you're only taking derivatives of the Lagrangian in that first term with respect to this term here. So it's easy to write, but you really have to be careful about what this is. In the case that I wrote up top there, it's actually the time derivative, second time derivative minus the del squared operator. And some people call this, is it like a, what else is this thing called, this box?
Degeneration.
What? The box thing, yeah. And so that gives you an equation that's, something you should be able to compare directly to. Box plus m squared I equals 0. What is that? What did I just write there?
Klein-Gordon equation.
Right, for a free particle of mass m. Where does the Klein-Gordon equation come from? I don't know if I can do this off the top of my head, but in principle, it's simple. So if you just write the relativistic expression for the energy in terms of momentum, m squared c to the 4th. And you substitute in, the expressions for energy and momentum that come from the time-dependent Schrodinger equation. Right? So E is a time derivative, and M's a space derivative. That's all your Klein-Gordon equation is. So from time and it's going to be I. It's going to be a time derivative there. And then just in general, your P, your momentum. That's right. Square those things, put them in that equation. And then you'll get, nope. And you know what? Set h bar equal to 1, c equal to 1, of course. Okay, let me keep the h bars in for one step. So it's h bar, it's going to be minus because you have imaginary. Second derivative. Minus So now, these are operators, act on your fields. And then you'll get the right equation. So you get time. We move this over here, so then it's minus del squared phi plus the mass squared, which multiplies the scalar field. Okay, that seemed too easy. But so the point is that when you basically derive the equations of motion for the phi-4 theory, you get the Klein-Gordon equation, which I guess isn't surprising because you have Lorentz invariance built into this expression, right? But what that gives you is the interpretation of your phenomenological parameter R as, I guess, minus m squared. That minus sign doesn't bother me. It just comes from the way you write the original action, whether you add or subtract the phenomenological phi squared term. So when you see this term in a Lagrangian in whatever context, that's what people call a massive term, or a massive scalar, or something like that. That's the same mass that when we set it to 0, we got this like critical expression, or this divergence of the correlation length. Okay, so when people are saying, is that a massive theory? Blah, blah, blah. That's why they call it a mass. But let's go back to our phenomenological. Any questions on that, by the way? Ooh, might have broke this. Does that twisted trail of logic make sense? Because it does to me. Okay, so let's go back. That was just all an aside. Why is it called a mass? So I want to go back to my phenomenological theory and talk about symmetry breaking in that theory. Okay, what is the appearance of the vacuum expectation value in the saddle point approximation? What does it mean? What does it correspond to physically? And a good context for kind of understanding the general principles of those types of theories, especially in condensed matter, are called Laudau theories. They're phenomenological when they're not derived from microscopics. And Laudau, in the original sort of treatment of these types of theories, really was considering general expressions for the free energy. Okay, so Russians, you should be proud of this. Introduced by Laudau. Way ahead of his time. Very general, based on symmetries. You don't even have to consider the idea that you have some sort of phi-4 action. Although, for the context of this class, we're going to relate Laudau theory to this phi-4 theory. So what Laudau suggests is that the free energy of any system should basically be analytic and observe the symmetries of the Hamiltonian, which is sort of the conditions I've been enforcing all along when you think of like how you're constructing which terms. You know, is there a phi squared? Is there a phi cube? Is there just a plain old phi, right? Phi 4, phi 6. All those terms should be reflected in the Hamiltonian symmetries. And if we interpret our functional, our Lagrangian density functional as a free energy, which I'll get to in a minute, then all we're talking about is sort of minimizing free energies. And that'll give us the phase of matter that we're sitting in, right? So the principle I talked about like in the very first class. So those symmetries can be very complicated. If you look at some recent work, say that like Sabir Sachdev or other condensed matter people have been theoretically looking at the pseudograph and the Krupp-Rates width, they'll derive a phenomenological Laudau theory that is very complicated sort of terms based on the symmetries that the symmetries of the Hamiltonian that they believe underlies it, or the broken symmetries that occur in the experimentally observed phase diagram. So some of these theories might be SO5 or almost SO5 symmetric. Some of the new theories that Sachdev works on and others are approximately, I guess, O6 theories. Okay, so just some symmetry of all the order parameters are approximately O6. That takes into account things like superconductivity, which is an O2 symmetry. We'll talk about that. That's also on your assignment. But you can cross that with another O2 symmetry for broken two-component order. So that'd be something near an O4. And then you can have higher order coupling terms, and you can have terms that have to do with, magnetism, which are typically O3. So all of those types of theories you can just form based on symmetries. And you would just look at sort of a free energy. So let's write, based on that philosophy, if I keep writing phenomenological, it's going to take me all class. So just write an expression. For the free energy as a Taylor expansion of an order parameter. So again, that order parameter has to be something that's motivated by whatever problem you're studying. It could be superconductivity, it could be whatever. It could be superfluidity, it could be the phase of the wave function, right? That could be an order parameter. In simplest Landau theories, typically the field, so the phi that I'm going to use the same notation as the field theory, is actually just a magnetization. So I can even imagine your Ising model. Your Ising model has an average magnetization that's a function of say, the lattice site or something like that, right? And I can, instead of labeling the lattice site, I can just label the coordinate. And in the case where variations of the magnetization are slowly varying, compared to the lattice length scale, then that discretization of the lattice doesn't matter. And that's sort of the regime in which these theories are valid. So the magnetization would be something like SI. Right? So like the sum of all of your Z component of your spins over the number of lattice sites. So. So the idea of having, continuum theory is really only justified in the case where, somehow the variations of the average magnetization, which is like your field, is long compared to the lattice height. So it's not like something that's completely controlled by lattice length scale physics. And you have to think about why that would be justified. And the reasoning behind that justification comes out more so in 705. Particularly near phase transitions or critical points where the correlation length chi or xi or xe, whatever this thing is, goes to infinity. Okay, so let's just assume that somehow we're in this regime. Yep.
If you go near a critical point, then the energy starts becoming singular.
Right. Yeah, that's what we're going to talk about now.
So how does Laudau theory work?
Well, so right at the fixed point, right at the phase transition, you lose that, analyticity. Yeah. That's why it's a phase transition, I guess. Yeah, so let's look at that. We can just write an expression for the free energy as a Taylor expansion over the order parameter. Okay, and let's look at how this condition of analyticity breaks down. Free energy, it's a density. It's a free energy density. It's not extensive. And we're not going to use this M, this magnetization, because it gets confusing with all these masses and stuff. But you can think of a magnet. So since we're talking about sort of condensed matter theory, the Ising model is the go-to model. Let me just write very generally. An expansion of my free energy in terms of powers of phi. Okay. And I've just labeled the coefficients with some arbitrary ANs. They're going to be constants, of course. So let me consider first for example, your Ising, ferromagnet. So it's minus J, I, without a field, without the coupling, that looks like this. Okay, so that's an interacting system of Ising spins. I and J are nearest neighbors. So you imagine this thing's on a very small length scale lattice. We've coarse grained this lattice out. Okay, and this Hamiltonian has an inversion symmetry. So it has a certain symmetry. If I flip the sign of the spin, Fz goes to minus Sz. then the Hamiltonian sign remains invariant because there's a product of them, so there's two minus signs. And so by Landau, that invariance should be reflected in the free energy. So for h equals 0, oops, it should be plus f of phi because of the Hamiltonian symmetry. So that means we can just eliminate all the terms that are odd powers of phi here. So the A1s, A1, A3, A5, all those things must be 0 if we have this symmetry. So then I have a very simple free energy. Which, of course, looks exactly like the mean field expression with no spatial variations in phi that I'd written like this. So that's the same as your potential term, not your kinetic energy, your potential term in your Lagrangian. Which makes sense. Because if you think of what we're doing, we're looking at a free energy, or free energy density, but a free energy is defined as minus Boltzmann constant t or 1 over t, log of the partition function. Right, and our partition function could have been written as this functional integral and in the saddle point approximation, we're just, looking at the value where this is maximized. So we're taking a logarithm, and so we can basically see how this thing's related to the free energy. In particular, the minima of the action should correspond to the minima of the free energy. And that's important because we know that we want to minimize free energies in order to see what state the system's in, right? So now we can start interpreting this Lagrangian density basically as sort of free energy in this approximation. And the state of the system will always sit at the minima of the free energies. Just like when we did the Peierls argument. Remember, we looked at the free energy. We were balancing the energy and the entropy term. And we wanted to minimize that thing. And correspondingly, the state of the system sits in that minimum. Okay, so now we can just look at the phenomenological theory as a theory in the free energy. So you're doing this on your assignment. You're looking at the minima of that free energy function, if phi is just a variable. So let me just do something slightly more complicated. If I add this field back in, then I should add a term proportional to phi. And maybe you can add higher order terms, but sort of in the spirit of Landau theory, you add the lowest order terms sort of necessary to capture the physics that you're after. So similarly here, you can add phi 6, phi 8 terms. You should plot the functionals and see whether or not it matters. I'll talk about that in a minute. So. the lowest order term that breaks this inversion symmetry. This is a useless equation, right? That's supposed to be minus. Breaks that inversion symmetry, phi goes to minus phi, which I didn't write down. All right. Let me write it below. So in a Laudau theory, I'm just going to add what does necessary mean? Well, usually we need higher order terms in order to keep our function bounded or something like that. Okay, so it comes from some other physical principle. Okay, so this is just slightly harder than your assignment 4, question 2, where you want to find the minimum of that function. There's two very different types of solution. So, as you're doing on the assignment, if your h equals 0, then the minimum of the free energy basically has one solution for R positive and one solution for R negative. So for R positive, the function is just as a function of phi. The free energy functional just looks like a warped, parabola. It's like a phi squared plus a phi 4 term, right? So the vacuum expectation value is just at 0. But if you change the sign of R, then the solution looks different. So there's two degenerate minima. So this is what you'll derive on your assignment. So your free energy has that shape. What are those minima in terms of the original interpretation as an Ising model? Right? Remember we had spontaneously symmetry broken phases at low temperature? And so that's the two possibilities. You have basically a positive and a negative value for the field. It's like the two ferromagnetic states.
Question about it. So at the beginning of the course, you talked about spontaneous symmetry breaking as something that happens in the thermodynamic limit.
Right.
Where does that assumption comes into play here? Because it seems that your free energy is proportional to the volume, right? And when you take that volume to infinity, it's not clear to me where does the assumption of the thermodynamic limit.
So that argument of spontaneous symmetry breaking is not in this theory, because that's the argument that you choose one of these or the other. But there's no way to choose that in this theory.
Or it has to do with the fact that if you're not in the thermodynamic limit, there's a finite energy barrier between the two.
Right here.
Minima, so that when you send it to infinity, you choose one and you can't go to the other.
Right. So the order limits that we took, well, I can do it next, in this theory would be like if you had a small symmetry breaking field, then okay, so if you had a small symmetry, so those are completely degenerate. There's no mechanism in this theory for choosing one of two of those one of those two minima.
Where does the 5-4 come from the Hamiltonian?
Where does the 5-4 come from? That's why you're driving on your assignment, right? Right? It comes directly from this Hamiltonian. So this is an interacting Hamiltonian.
Right.
This is like the most fundamental sort of interacting Hamiltonian.
So wouldn't that correspond to phi squared?
You get a 5-4. Yeah. That's why I made you do it on the assignment, so you'll always remember.
Some things before you proceed. So
yeah.
In that interpretation you gave with the exact order equation about R, it seems to be that R can have only one sign. Plus or minus, right? Because you're relating R to M squared. So, I mean, the mass cannot be complex. Right? So then, I mean, if you go to R going to negative, what's the interpretation of R in terms of the mass? Or there's...
Well, so wasn't R minus
M squared, but if you're in real time, so if you go to Euclidean time, then R is like M squared. So R is positive, which means that you're in the symmetric phase.
Right. So R is positive. So, yeah, so if R is positive, you're in this phase, you're saying.
If R is positive, you're in the other one. Right? In the symmetric one.
Oh, yeah. This is the one with no symmetry breaking, right?
Yeah.
So what are you asking, sir?
So what does it mean that R is a negative one?
So what's it mean in terms of the mass?
Yeah, the question is whether there's an interpretation in terms of a mass or...
There's an answer to that question. I just don't know what it is. Let me think about it. Yeah, so you don't want to have negative, or you don't want to have imaginary masses, right? That's what you, in principle. So these, yeah, so this should be the value of your mass. This should be the sort of value of your, this vacuum expectation value, what you're calculating. Yeah, let me think about it. There's definitely an answer to that question. So all I wanted to say was, okay, so we'll get back to that. So this gives you the two degenerate ground states that correspond to, the magnetizations, all polarized up, all polarized down. You don't have the mechanism for spontaneous symmetry breaking necessarily in this picture. If you put on a field, what you do is you skew the shape of these things, right? So the field couples to, have a minus sign in front of it, right? So it lowers the energy for this type of configuration here, which is the positive phi configuration. So for R greater than 0, what happens? It looks somehow like this, I guess. Right, so that's your F, that's your phi. And for this case with symmetry breaking, okay, so there's a symmetry broken, if you will, but it's a symmetry that's in the Hamiltonian. Okay, so the symmetry of this phase is the same symmetry as the Hamiltonian. That's the way you should think of this. In this case, the symmetry of this phase is the same symmetry of the Hamiltonian, the paramagnet. Right? Here, the symmetry of the phase is lower than the symmetry of the Hamiltonian. So the symmetry's been broken. That's why it's called symmetry breaking. In this case, also, you'll pick, it'll look like this, I guess. Yeah, it'll look like this, probably. You'll pick a minimum of the field. That's an absolute minimum. So you can think of this spontaneous symmetry breaking, the order limits that we took at the start of class, is somehow taking a limit first, where you have a magnetic field, you're in the thermodynamic limit, and so you'll find yourself in this minimum here, and then slowly taking the field to 0. Then you'll be back in this case, but you'll be sitting in this one, and there's an activation energy, which you're going to calculate in your assignment, that you basically can't get over when you're in the thermodynamic limit. At 0 temperature, especially. There's all just sort of general arguments about the symmetry. But what's going on specifically at R equals 0? Right? So when you transition between this case or this case here. So very generally, there's a phase transition. R has to tune you through that transition somehow. So if you're thinking about, the microscopic Ising model, you know how you tune through that transition. In 2 dimensions, say, it's by varying the temperature. So somehow that R has to have that temperature encoded into it. It's like the fundamental parameter that measures your distance from the phase transition. And I'll call that phase transition temperature Tc for critical point, which I'll explain. Okay, so how does the temperature dependence of R come in? Well, when you do the Laudau, like the expansion here, you can basically just imagine that every one of these parameters has some temperature and some field dependence in it. And then from the physics of the system, you just, phenomenologically determine what that functional form is. So I'm not calling them A's anymore. It's my R's and U's. Temperature and field, they can be Taylor expanded. Everything's just a Taylor expansion within a Taylor expansion until there's nothing left. And so these parameters, like say R, it's a function of temperature in this case. Let me promote the phase transition like this with the temperature. So some constant, some term that's T minus T, then plus higher order terms, T minus Tc squared. Same with U. And to determine what these parameters within parameters are, you just have to ask what's going on. We need R to be a monotonic function that flips sign when we go through the transition. So it means that this R1 has to be 0. R1 equals 0, and R2 is just some parameter. And when R is negative, okay, so when it flips that sign as you go through Tc, you still want your free energy to be bounded. You don't want the whole thing to be upside down, right? And in order to have this type of shape here, you need U to be basically constant, which is greater than 0. Its temperature dependence comes secondary. If U flips sign, then we have to add another term in order to keep the free energy bounded. Right? So even though I flipped my sign of R, so this is like my parabolic term here, my fourth order term still at long distances keeps my free energy bounded. But if for some reason I flip that term, it's a different theory. Then I have, both those terms are upside down. I need a phi 6 or something like that to keep everything bounded. So the shape of the free energy as you go through that transition tells you something about what they call the order of the transition. So how does those vacuum expectation values say, how does this evolve? Well, I don't know, the best way is just plot that function out for different values of R. So for large, R greater than 0, you get something like this. For large R less than 0, you get something like this. And for intermediate values, okay, so what you're doing is you're tracking the minimum of this free energy to tell you your phi bar, right? So for some intermediate value here, you can imagine, I don't know, that minimum value being slightly closer to 0. And what happens exactly at the phase transition is, you basically flatten out that functional quite a bit. And this one, I should use a different color. That's R equals 0, which means T is equal to TC. So then your phi will move continuously from 0 to the vacuum expectation value. Phi bar is a function of T. Will look something like this. It'll be 0 until you hit the transition temperature. That's TC. Okay, again, that's like tracking the minimum here. So that's a continuous phase transition.
Is this, why is the mean field positive or negative? Should we say 0?
Well, it's 0 in the way that if you average these two things, it's still 0. Right? But we're assuming some spontaneous symmetry breaking.
Oh, so not.
Yeah. So you have another solution that goes like this.
Right.
Yeah. So it's like you've tracked down, I don't know, you've tracked down and then spontaneously symmetry broken into one of these two states. Yeah. So it's the same argument here. You basically have to have a small symmetry breaking field, which in the general sense is you need a...
But here it's not spontaneous.
Yeah, so spontaneous symmetry breaking means you take this limit to 0 first, and then the thermodynamic limit. So physically what you get is a magnetization. When your ferromagnet is polarized, it means you've already had spontaneous symmetry breaking. And so, again, yeah, you can have two solutions, but I'm just assuming that only one is chosen. Yeah, it's a strange mechanism, right? Like spontaneous symmetry breaking.
Why did we need the mean field?
So it's called mean field theory because what have we done?
We've just written the free energy as some Taylor expansion of
Yeah, so we have no spatial variation of phi. So there's just a phi term. So we've ignored any sort of, we either have, we don't have any sort of necessary information about the spatial variation in it. Yeah. So it's like you've averaged over all the spatial variations to just get a mean value, right? So the magnetization might not be 1 if you have some little minority spins in there, but all we're considering is the mean field. And so that's why you get like some mean spatial field. So that's why you get values that are less than 1 or 0 there. So mean field refers to basically the saddle point approximation, the simplest classical extremizing of the action. And if you put a fluctuation on this thing, which you'll do in your assignment, so now you start in the mean field value, or the mean field solution, and then you add small variations around this minimum. That's your like phi prime. That's your Gaussian, that's your fluctuation theory. So I don't know who names these things, man, but I think the sort of field theory and the Laudau language are kind of confusing maybe if you mix them together. Okay, so I'll talk a little bit more about what these continuous phase transitions are, and then we'll look at some first order terms. I want to flip the sign of U and actually see what happens to the Laudau functional. So in that case, you get your other type of phase transition where this order parameter evolves discontinuously through the transition. So that's the other thing you see in nature. You see, continuous transitions. This thing's a critical point. It has a critical theory with a divergent correlation length. This is what's really interesting. This is like the liquid gas, transition. It's the same universality class as all these other transitions. There's a conformal field theory that describes it. This is what Zamolodchikov was talking about. Then you have cases where this thing's discontinuous, where it jumps right at the transition temperature, and those are completely boring. They basically don't have any sort of interesting critical theory associated with them at all. So we'll just use this phenomenological theory and look at those at the start of the next class. Okay, awesome. See you then.